We take air travel for granted. Around the world, there are millions of aircraft movements every day. And the reason it's so safe is that planes are routinely tested to their limits. Here, this plane wing is being stretched to extremes to see how much it can take. It finally succumbs at 1.5 times the amount of stress it was designed for. And here a plane is trying to take off 30 miles an hour below its normal speed. It slows itself down by scraping its tail along the runway. And it makes it. This drop test, conducted by the American Federal Aviation Administration, examined the forces involved in a crash landing. These tests and thousands more are filmed from every conceivable angle and then analysed over and over again by the crash testers. Their work has made air travel the safest form of transport on the planet, but it wasn't always that way. The world's first jetliner, the Comet, suffered from design flaws in the 1950s, but the numerous crashes taught engineers many lessons, and it's only down to testing that air travel has become so safe today. But planes do crash, and when they do, fire can be a bigger killer than the impact itself. Fire spreads rapidly in crashes because the fuel turns into a highly flammable mist. In this staged crash in 1964, the fuel becomes explosive as it mists, behaving almost like a gas when it touches an ignition source. The plane is engulfed in a fireball. So the Federal Aviation Administration developed a new fuel that behaves quite differently.
The results of the test to date are reported in this gelled fuel report.
This fuel, called anti-misting kerosene, or AMK, contains resins that prevent the fuel from turning into the deadly flammable mist when released. In this comparison, the bottom of the screen shows AMK sprayed over a flame. The same amount of normal fuel is sprayed in the top half of the picture. The AMK doesn't burn. And in this test, normal jet fuel is loaded into an external fuel tank and dragged along a runway at 30 miles an hour, passing over spikes to rupture the tank. A continuous flame beneath the tank eventually ignites the fuel. Do the same with AMK, and the fuel doesn't burn because it keeps its gelling qualities when it's spilled.
There is no fuel ignition.
They were so confident of success, they decided to try it for real. Here in the Mojave Desert in California, work began in 1969 to stage a controlled air crash. It took 15 years of planning before the teams were confident of success. William Westfield was the FAA's chief engineer on the test.
It certainly is an odd feeling coming back to this site after 16 years and not having been here in the in-between time. But it brings back an awful lot of memories about what happened and what didn't happen in that so-called controlled impact demonstration, which turned out not to be so controlled.
With the help of NASA, hundreds of gallons of AMK were pumped into the plane's wings in preparation for the test.
My role was primarily to make sure the fuel was acceptable, to make sure that the aircraft was acceptably configured. We knew that we had a fuel that could possibly prevent the misting that occurs in most aircraft crashes. And what we wanted to do was bring an aircraft down hard and break open the wings.
So they built a specially designed runway in the desert.
The crash zone was covered with trap rock. That would give us plenty of ignition sources, sparks, and things like that. We built monstrous obstacles in the path of where the aircraft was going to hit. We referred to them as rhinoceros. And we said it all depends now on getting that thing to come down where we wanted.
NASA decided to take the opportunity to test lots of new equipment, including stronger seating, new black box flight recorders, and fireproof seatbacks. 2 test pilots volunteered to fly the plane, but NASA decided not to risk a real pilot. Instead, they devised a system to allow an experienced test pilot to fly what became the world's biggest remote-controlled aircraft. The plane's engines had to be modified to convert the gelled fuel back into its original flammable form so it could be used. Any damage to these engines could expose fuel and render the test a failure. In fact, the engines were to become the test's Achilles heel. Find out what happens later when the plane comes down. Thankfully, plane crashes are rare, but car crashes kill thousands every year. Testing cars to destruction is far more straightforward, but what's not so well known is how the testing began. The car is by far the most common technology on the planet, but it's incredible to think that once there were no seatbelts, no airbags, not even headrests. The statistics told the story. By the 1950s, over 5 million people had been killed on the world's roads. But now the car is a safer place to be than ever, and that's thanks to the contribution of a small team of crash testers from Michigan. Bud Mertz was part of that team.
I find myself feeling I've been very fortunate to be placed in a position where what you do has meaning. Being able to say that, yeah, you saw it started from the beginning and you see the fruits of the labor some 30-odd years later, 40 years later, that's great. There was quite a bit of work done back in the 50s in terms of analyzing field accident data. It became apparent how people were dying.
Bud's team had very little to go on and had to start almost from scratch.
All systems are go.
In those days, there was no data as to how the human responded.
No one had ever studied car crashes in such detail, and since only the simplest of crash test dummies had been developed, there was only one thing for it: ask for human volunteers.
Usually it would be the principal investigator, in this case Professor Patrick, who would volunteer to do the sub-injury work. Majority of the time he would not let us students until he had volunteered himself.
I rode the sled about 400 times. When I drove a car into the wall at 12 miles an hour, for example, it felt like my head was coming off. And there's no way you can support yourself against the steering wheel with your arms at 12 miles an hour. You're just not strong enough.
Many of the safety improvements of the past 30 years are a direct result of this research.
As I recall, the number of fatalities per 100 million miles driven was about 12. It's now down to about 3.8 fatalities per 100 million miles driven. A lot of that is due to the improved dummies.
In Larry's day, windscreens were made of just ordinary glass. This caused horrific and disfiguring injuries. One test required Larry's skin to undergo some extreme punishment.
Another contribution was the energy-absorbing steering column. This had a major impact on thoracic injuries that were occurring in vehicle collisions.
But the car manufacturers needed to be able to repeat extreme tests time and time again, and couldn't use human volunteers for obvious reasons.
Finally, I was told by a neurosurgeon I was working with. He said that he could see lipping on my spinal vertebra and said that, stop now.
But the volunteer program had told them enough, and they came up with a new crash test dummy called the Hybrid 2. It was the first dummy that was specifically designed to survive more than one accident.
We did all the testing to demonstrate that it was reproducible and repeatable. The Hybrid 2 was put into the standard in about 1970-71. But at that point in time, it was apparent that the dummy did not have the human-like characteristics that we wanted.
So Bud and the team started work trying to improve the Hybrid 2. They came up with the Hybrid 3.
It took till 1997 for the Hybrid 2 dummy to be deleted, and at the present time, only the Hybrid 3 dummy was to be used for restraint system testing. The Hybrid 3 dummy also became the dummy that's used in all the safety standards and all the safety testing for frontal restraint systems throughout the world.
The pioneering discoveries made by Bud Mertz and Larry Patrick are still having a major benefit today. Using the same principles of crash testing and measurement, this team are about to crash a £15,000 car into a concrete block at 30 miles an hour, an impact that would cause human occupants serious injuries. But thanks to Larry Patrick and his team, 2 Hybrid 3 dummies will be reporting any injuries. The crash will be recorded by over 30 ultra-high-speed digital cameras. The dummies, cameras and electronic equipment have to be installed with complete precision if the test is to be considered valid. Today they're testing the deployment of airbags, but tomorrow it could be seat belts, crumple zones, or even the dummies themselves. Over 4 hours of preparation will culminate in an event lasting less than 80 thousandths of a second, a fraction of a moment that could decide whether you live or die. And when everything is set, the car is towed back to the start line, ready to be hurled into the concrete block at the end. In slow motion, the damage to the car is clear. First contact between wall and car happens now. And after just a blink of an eye, it's all over. The airbags deploy correctly, and the test is deemed a success. When it was developed, the Hybrid 3 dummy was exactly what the engineers were looking for. It told them everything they needed to know at the time. But the car has evolved, and so must the dummy. Soon the Hybrid 3 will join other early dummies in motor museums, because even it's considered not to be sufficiently human-like, a characteristic now known as biofidelity. Meet the new generation, Thor.
The development of Thor started in January of 1995. A lot of the Hybrid 3 technology was kind of becoming outdated, so Thor was kind of created to increase the biofidelity of Hybrid 3.
Each version of this highly advanced crash test dummy costs around £40,000. It was developed by a team of engineers from Baltimore, USA.
And go! One of the first areas that was targeted was the rib cage, because the Hybrid 3 dummy has a very squarish looking rib cage. It's not very human-like, and the instrumentation in the rib cage only measures the deflection at a single point. Other areas of the dummy which were upgraded include the shoulder area to try to make the motion of the shoulder more human-like, and we reshaped the neck. We're able to control the head motion much more accurately and make it much more human-like.
When airbags started to appear in cars in the 1970s, the pattern of injuries changed. So the dummy designers had to think again.
With the advent of airbags, this devastating injury that was seen in the 70s when people were crushing their rib cage and stuff is no longer seen. Now people are having to go through a lot of rehabilitation with lower leg injuries.
And the testers now believe it's better for you to break a bone than snap a tendon in your leg. Tearing muscles and tendons means months rather than weeks of immobility. So Thor's leg has been designed to investigate these specific types of leg injuries.
With Thor, we've added rubber elements that can be tuned so that you can correct the motion in inversion, eversion, which is the side-to-side motion of your foot, as well as a dorsiplantar flexion, which is the fore and aft movement of your foot, and also incorporated the motion to do internal and external rotation, which is sort of that rocking you can do with your ankle joint. This lower leg also includes a representative Achilles tendon assembly and help keep that motion as human-like as possible.
Thanks to Thor and to the early pioneers, you can now drive to work confident that you're much more likely to survive a car crash than ever before. And their work has meant that dummies like these are a standard tool for crash testers everywhere. Here, dummies are used to test new airbag technology for motorcycles. If you're in a car crash, you're likely to injure your legs. If you crash your motorbike, it's your head that will suffer the most. But of all the car accidents you could be involved in, the one you don't want is to have a head-on collision. So to keep you on the right side of the road, they invented the crash barrier. Once again, some of the most important research was carried out in the 50s. Construction is everything. Placing the barrier supports too far apart allows the metal to twist on impact and vaults the car right over the rail. Just by halving the distance between the supports makes all the difference. Using the wrong materials also results in problems, as does failing to properly secure it at both ends. Flexible barriers made of steel rope and chain link fencing have early design problems. Drivers of convertibles would have lost their heads. Improvements were made, but then the fence was too weak to stop the car at all. But with perseverance and many years of testing, this revolutionary rope fence was developed in 1991. It's made of carbon steel and can withstand a force of over 80 tons. And it stops this vehicle getting a soaking. But there are much bigger vehicles on the roads. This driverless petrol tanker is propelled into a concrete barrier. At 40 miles an hour, the barrier isn't strong enough, and both the lorry and the barrier crash down. Had this not been a test, fuel would have leaked out and there would have been a disaster. So the testers made the barrier twice as thick and tried again. The lorry hits at the same speed and angle, but the barrier stays put and the lorry stays upright. The barrier gets approval for use on the road. Another test, another tanker, driven at 50 miles an hour to examine the strength of a new bridge. Total destruction for the bridge support, the lorry, and had there been one, the driver. We've all driven away with a cup of coffee on the roof of the car, so what happens if the lorry driver forgets to lower the tipper? Fortunately, the bridge is stronger than the lorry. So how about a badly loaded digger? The bridge looks okay, but it did need some repairs. Repairs to bridges cost millions and cause untold delays, so a rail company wanted to prove a point with an old school bus. If you were sitting upstairs, you wouldn't stand a chance. The testers don't stop there. They make sure that when what they call road furniture gets hit, it gives. So whether you collide with a street light, or a road sign, or the central reservation, you know that the materials have already been destroyed many times for your benefit. And now the testers are turning their attentions to pedestrians. Believe it or not, they're trying to make being run over more survivable. Engineers are especially concerned for the safety of children. If a child is hit by a car, the injuries are similar to that of an adult being hit by a lorry. The roads are a dangerous place, especially if you're a police officer. A police patrol vehicle follows a speeding car near Atlanta in Georgia. It's a routine task that Sergeant Henry Huff and the world's police officers perform every day, hundreds of times.
Most traffic stops are just normal. You go up there, driver's license, insurance, it's what you're doing. Either cite them or not, let them be on their way.
But in January 1997, Officer Huff picked the wrong car. Nothing prepares him for what happens next.
Hello, sir. The reason I stopped you doing 88 miles an hour. 55.
Everything was like real quick. I know everybody wants to drag it out, but I never saw the gun. It was just, never saw the flash of light. I never seen any of this stuff. It was just like, whoa. I took a cover position, did fire back upon the vehicle, and the vehicle drove off. At that time, I proceeded back to my vehicle. I called, told them what had happened, that I'd been shot. I needed an ambulance to come to my location.
Officer Huff should have been killed, but in fact, he was wearing body armor.
This is the vest we wear, the body armor. As you can see, if I'm wearing it, the proximity of where both rounds had hit did its job. It's made to stop rounds, and it did. This is what the inside looks, solid. Right here is where the round hit. It grabbed round. Also in this area is a steel plate. The plate goes over your vital organs, and it's just extra protection. As you can see where this round hit, it made a big dent in the plate.
Officer Huff owes his life to this technology and is back on patrol, keeping the roads safe. His vest was developed and tested here in Jacksonville, Florida.
Body armor is designed to be effective against handgun cartridges. A good example of a very popular handgun cartridge is the 9mm. That was the round that was fired at Officer Huff. Inside is the ballistic element, and what's actually inside of this is the ballistic material itself.
The vest is made up of dozens of layers of densely woven materials, mostly polymers. They work collectively to slow down and eventually stop the bullet.
In order to stop a bullet, we need to absorb the energy. And so having a high tenacity, non-woven material on the front, we're able to start to absorb the energy of the bullet, to begin to change the shape of the bullet. In order to ensure that the vests work when they hit the street, we will randomly sample the completed model, take it into our ballistic lab, and test it to destruction. The reason that we test so often is because this is life-saving equipment.
Tom Dragone, a ballistics expert, considers the test a success if he can find the squashed bullet.
Let's examine the vest. Cut the cover open, and we can pull the actual ballistic filler out. And there's the bullet. The vest has done its job. Actually, it stopped on the first ply. But you can see where the energy is absorbed by these lines. And we go to the second ply and subsequent plies, and you can see less and less of a disruption of the material. And as you can see, the bullet is deformed, the energy being absorbed by the ballistic system. That's what body armor does.
They're like second nature now. There's no reason you shouldn't be wearing them. And to the people who do make all the body armor, I really appreciate it.
Body armor was developed by the military to protect their soldiers, but they haven't stopped there. They've always been the great innovators of the testing world, but things don't always go so smoothly. During the American hostage crisis in Lebanon in the 80s, the Air Force developed a new short takeoff and landing system for its transporter planes. They attached rockets to this C-130 Hercules. It gets away fine. But when it comes into land, the rockets fire too early, literally tearing the wings from the plane. Even when the military take the pilot out of the equation with smart weapons like this Tomahawk cruise missile, they still need to be tested. Collateral damage during a war can be a public relations disaster, as well as an unnecessary loss of life. This Tomahawk was launched off the coast of Southern California. It was programmed to fly a land attack mission over 500 miles and hit a communications bunker. During the course of its journey, the missile flew down valleys. At one point, it got as low as 200 feet. But, as expected, this Tomahawk hits its target with pinpoint accuracy. But to take things further, the Australian Navy wanted to test the accuracy of a torpedo fired from a new submarine. So they got hold of a used warship for the test. It hits and sends debris 500 feet into the air. But for a final word on weapon testing, nothing surpasses this test carried out by the American government in the 1950s. They built a whole town in the Nevada desert and then rigged cameras to film it be destroyed by a nuclear bomb. The testers wanted to see how a typical community might survive a nuclear blast. But first they had to build the typical town, complete with electricity substation, radio station and petrol station with a partly filled 18,000-gallon tank to test its strength. Different types of houses were built, including a concrete single-storey, one which should be tougher than most. The testers then put dummies into fully furnished interiors and others in direct line to the blast to test their clothing. No detail was overlooked. Real food was even put into the refrigerators. And then selected journalists were invited to watch the blast.
Observers without goggles must face away from the blast. H-minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
The bomb was twice the size of that used in Hiroshima. The electricity substation survived the shock, but other structures were not so strong. Though the new single-storey concrete home did well, electricity pylons, though knocked over, still worked. And as soon as power is restored, the radio station starts up again. The petrol tank and fittings remained intact. The dummies didn't fare so well. Nuclear testing in the USA came to an end in 1992, but these kinds of tests actually taught scientists that nuclear energy can be harnessed and used for man's benefit. The problem is the waste, and in the case of nuclear waste, it's deadly. It needs to be transported safely to a nuclear dump until it becomes benign. So the flasks that carry the waste mustn't leak. They have to be tested, and tested again. In early tests, the flasks were filled with water to look for leaks and then dropped. Here you can see that the flask has begun to leak. Improvements were made, and then the testers got serious. They tried dropping the flasks from even greater heights. And then they took other flasks out on the roads, strapped them to a lorry, and drove them into concrete walls. Still not satisfied, the testers then drove this 200-ton train directly into a flask.
Cask deformation was minimal, and the ability of the cask was not compromised.
This type of test became popular. Here, a British team abandons one of their nuclear flasks on a railway in Leicestershire and sends a train down the track towards it at over 100 miles an hour. The flask survived the tests intact, even though nothing else did. Occasionally, train accidents do happen, like this one in Paddington, which cost 30 lives. So to improve safety, the railways have always been the subject of extensive testing. In a crash, the greatest danger is when one train climbs over the other, squashing passenger compartments. So engineers are adding crumple zones at each end to absorb the energy of the crash. The crumple zones do their job, they crumple. But train testing like this is not cheap, so in future more testing will be done using computer models. In Pueblo, Colorado, a train carriage is about to be crashed into a wall so that the testers can write the appropriate software. At only a modest 35 miles an hour, any unrestrained dummies are hurled into the air. And the crash provides an invaluable amount of data to ensure that future tests will be conducted on virtual railway tracks. But some things on a train will always need testing for real. Train windscreens are still handmade. The process has to be perfect. If the glass fails on the train, the driver might be killed, so samples are always tested. A chunk of steel is to be fired at this sheet of glass at 180 miles an hour. The windscreens seem to have worked, but that's not all. Any fragments of glass entering the driver's compartment would also cause injury. So to pass this test, the glass also has to be intact from the inside. And it is. For airplanes, the biggest threat to flight deck windscreens is a bird strike. In a test, the canopy from this military aircraft fails when a real chicken is fired at it. The pilot might not have survived. But after more research, the testers came up with a flexible windscreen, which gives when the chicken is fired at it. If the worst happens, the testers need to ensure that the pilot's crash helmet stays put or stays in one piece. But if both the canopy and the crash helmet fail, then the pilot would normally be thinking about an unscheduled landing, something that the testers of all aircraft have spent years investigating. And in this real emergency, the helicopter pilot only just walked away.
In every accident, there's three types of impacts. The initial impact is, of course, the aircraft, in this case a helicopter fuselage, impacting the ground. The second impact is when the occupants possibly strike the instrument panel. Acceleration in the head can induce the brain to hit the inside of the skull, which is the tertiary impact of the collision, which causes brain damage. So if you can stop those injuries, you can save about 30% of all the fatalities in survivable accidents.
Here in Phoenix, Arizona, the testers are dropping crash test dummies to investigate the forces experienced when a helicopter crash lands.
During the test, we're going to raise the drop cage up to a height of approximately 30 feet and simulate a very hard crash landing.
They're testing technology with which we're all very familiar and could come into contact with any day.
Just as an automobile airbag protects a driver during a crash sequence, a cockpit airbag protects the pilot during a helicopter crash sequence. In a recent commercial helicopter crash, the only occupant killed, in fact, was the pilot, and he died as a result of a face strike on the cyclic.
The cyclic is the control stick on a helicopter. In this slow-mo, the crash test dummy's only injury was to his head when it hits.
It's those type of preventable injuries that a cockpit airbag system can prevent.
In this test, the airbag system has been disabled so the engineers can see how much the dummy's spines and necks travel at impact.
They'll drop from 30 feet, they'll impact at about 55 kilometers per hour, and they'll experience about 50 Gs of decelerative force.
On average, human muscles can withstand only a 3G impact. A 50G impact would multiply the weight of your head 50 times.
So we can expect severe accelerations in the head, severe forces of extension on the neck, and we're going to see some compression of the chest cavity. Okay, what we're going to do now is connect up the final wires. We're almost ready to do the drop test, and then we're ready to go.
The testers hope that the airbags might one day make it into other aircraft.
Well, eventually this technology can move out of the cockpit into the passenger seats and eventually into the passenger seat of commercial airliners.
In the slow-mo, the dummy's head strikes his knee. If it had been in position, then the cyclic would have caused serious injuries. So with airbags, a crash landing might one day be survivable. But some aircraft accidents would appear to be completely unsurvivable. This was a test, but this kind of thing does happen for real. Like in Scotland in 1989, when Pan Am 103 was brought down by a terrorist bomb. The testers went to work to see if they could make a plane bomb-resistant, and once again they turned to the crash test dummy. This explosion in New Mexico was a test to investigate what happens when a car bomb explodes. Everything is destroyed. This car bomb weighed in at 350 pounds. Imagine what a bomb this size could do to a plane. Pan Am 103 was brought down by explosives weighing less than 1 pound. The FAA carried out extensive testing to determine how to contain such an explosion. They started with a reconstruction on a disused passenger plane pressurized to the equivalent of 30,000 feet, as it would have been in flight, and then trigger a bomb hidden in the hold. Just as the testers had thought, the cargo hold was a vulnerable area. The investigators tested the same amount of explosive as used at Lockerbie in an everyday airplane luggage container. It fails spectacularly. So the testers are lining luggage containers with a synthetic blanket similar to body armour that allows the shockwaves through, but contains the debris. British explosive testers have placed a bomb in the cargo hold of this jumbo jet. They then line the front cargo hold with a new bomb-resistant material and repeat the test. You can hear the bomb, but you can't see it. Testing planes has always been a priority to maintain public confidence. Some of these tests were carried out for the anti-misting fuel experiments in the Californian desert in 1984, probably the most amazing plane crash test of all time. This plane was fueled with a new type of non-flammable fuel called AMK. William Westfield was the chief engineer.
We had 2 bona fide offers by pilots to take the aircraft in.
NASA decided not to risk a real pilot. Instead, they devised a system to enable an experienced test pilot to fly what became the world's biggest remote-controlled aircraft.
People at NASA did a wonderful job. They were able to control this aircraft, and in fact, I think something in the excess of 60 approaches were made. And on several of those approaches, it was so precise that they were able to touch the wheels and then go around again. I guess what kept going through my mind all along was, did we cover all the bags? Did we do everything we could? We knew the fuel was good. We knew the test was designed properly. The takeoff of the aircraft was perfect. There was no problems whatsoever. And it made its circular course around to line up with the crash site. In so doing, it lined up off to the right. And as it approached the crash site, the pilot attempted to bring it back on course.
But he was too low and didn't have enough time to get the plane back on target.
My comment to myself, and I know I said this out loud, was he better go around because he's not lined up. And I guess within seconds after that, I heard voices all over the control room saying, "Go around. What's he doing? Go around." He hit about 150 feet to 250 feet short of the target zone. And when he did, the left wing and engine dug in, skewed the aircraft to the left, and it slid through the crash zone, through the cutters and everything. I felt like somebody had kicked me in the stomach in plain words, because no way in the world can you do that to a fuel and expect it to last.
So why did the AMK catch fire?
The NASA management were concerned that since there were a lot of spectators that came on the base to witness this test, they were worried about the go-around capability. And rather than rely upon the work we had done in the past, they impressed on the pilot that it would be best if he could bring it in on the first shot.
After months of practice and dozens of dry runs, when the time came for the pilot to get it right, he got it wrong. The plane came down at an angle and the cutters sliced through the engines instead of the wings. The fuel was in its flammable form in the engines.
Although the test was not a controlled test and it was considered a failure, there were a lot of positives that came out of it. The crashworthiness equipment that was put on board, the energy-absorbing seats, the fire-resistant fabrics on the seats, the structure of the flooring to prevent the transmission of shock up to the passengers, the data flight recorders, which collected a lot more information than we had gotten before. All of this are positives and came out of that test.
But NASA deemed AMK to be a failure.
We plugged in all of the research costs, all the modification costs would have to happen at the refineries and the production costs and everything. And when everything was done, based upon a 1,500-mile flight, say from New York or Philadelphia to Chicago, you would increase the cost of a ticket by about $3.95, which shocked us tremendously. We thought it would be much more than that. The potential for the fuel to work is there, and the potential for a crash is still there. So if you can save half the lives, do it.
No one would expect an aircraft to hit a building, would they? But during the construction of New York's Empire State Building, an Air Force plane flying in thick fog crashed through an upper floor.
An account was made, 3 crewmen were dead, as well as 10 persons working in the skyscrapers.
So when safety fears were raised over the ability of a nuclear power station to withstand an impact, the testers really went to town. They flew an F-4 Phantom fighter plane into a concrete wall at 500 miles an hour to show who would come out worse. The wall won. The fighter seemingly disappears into thin air. In fact, it literally disintegrates. If this had been the side of a nuclear power plant, there would have been no safety scare. Though it's great to watch, testing like this is all about saving lives and preventing injury. Developers of the world's newest technologies like robotics, cybernetics, cryogenics, all benefit from the experience gained in crash testing over the last century.
10 seconds, go for main engine start.
But the next century will be all about space travel. Humans will start to live and work more and more in space.
And lift off.
But because it's such an alien environment, the risks are even greater than on Earth. So when the space shuttle suffered its only catastrophic failure in 1989, even NASA had to go back to testers for answers. They tested every piece of the shuttle's engines to destruction. And the shuttle has been flying without a hitch ever since. Thanks to the testers, our lives are safer and more enriched than they've ever been. And the next time you travel anywhere by road, rail, plane, or even spaceship, just remember that everything, even the TV you're watching, has probably been through hours and hours of testing to destruction.